Hello friends, in today's class we are going to talk about non-contiguous memory allocation scheme, which will be including discussion of pages and frame. So welcome here, and we are talking about non-contiguous memory allocation. We have already seen the contiguous memory allocation. And contiguous memory allocation suffers from the problem that is your internal fragmentation as well as external fragmentation. Okay, and here one of the severe requirement is that the memory that should be contiguous. That if I want let's say 500 kilobyte of the space, then this should be assigned in a contiguous manner. Okay, so if I do have a space of 500, but I have space something like 200 kilobyte in one space, and suppose 300 kilobytes in another space, but still I cannot allocate because the requirement it should be contiguous. So both the external and internal fragmentation comes here, and we have already seen that it can be solved by using compaction, but again it's a very costly operation. Okay, costly operation. Now here, since the processes are swap in and swap out, okay, that is swap in and swap out from disk, then disk also suffer from the problem of fragmentation. Okay, disk also suffer because that you have to also manage. Disk also suffers from fragmentation problem. Okay, so that the disk space that has been allocated also suffer from the fragmentation problem, and here compaction will say that it is not possible here in this case. Compactions is not possible because it's extremely slow in disk. Okay, extremely slow in disk. Okay, so that is something that is one problem with this contiguous memory allocation. Okay, so that is the several reasons are there, and for that another method has been developed or discovered, that rather than having contiguous memory allocation, let's divide the entire memory into some fixed size block. Okay, so let's have a fixed size chunk, fixed size block, and let's divide the memory, the logical memory, okay, the logical memory, the physical memory, as well as the disk. Okay, let's divide them. Okay, and that is the core idea of this non-contiguous memory allocation. Now here we have few new terms. The new term is your frame. The new term is your page, and these new terms are somewhat related to the previous explanation, that we are dividing into some fixed size blocks. Okay, so first thing that we'll do, that physical memory is broken down into a fixed size block or frame. So that fixed size block for physical memory, okay, physical memory is called as frame. Okay, pages, logical memory, that is the memory, the address is generated by the CPU or let's say the compiler, also broken down into a block of same size called pages. Okay, so page is for logical memory, and do remember this point. Page is a logical division. It's a division of logical memory, and frame is for the logical division of your physical memory. Okay, so when process is executed, its pages are loaded into the available memory frames, okay, from the backing store. Now when the process this is very important part, when a process executes, we'll take this for that pages, we take from the, where we'll take from the backing store or the disk. Okay, from the backing store will, or the disk will bring the page and load where, load into the frame. The backing store is also divided into the fixed size block, and that same size fixed size blocks that are of the same size as the memory frames. Okay, so backing store is also divided into that fixed size block. Okay, so non-contiguous means what? Non-contiguous memory location means now we have a scenario that entire memory is being broken down into a fixed size block, and now we have, suppose first reference is that you required 500 kilobyte. Okay, and we have non-contiguous spaces in different place, and this is the process P1 that required. So what we can do here is that here the availability is 200 kilobyte, here availability is 300 kilobyte. So what I can do here, I can say P1 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 P1. Okay, so now we are dealing that the larger part, internal fragmentation. So still we are not able to remove internal fragmentation, will be still there, but because now we have removed the criteria for this being contiguous, so in that case we will definitely take the advantage and we can tackle somehow the external fragmentation. Okay, external fragmentation, but because of this it may be possible your internal fragmentation will increase by significant amount, but that is the trade-off between contiguous and non-contiguous, and we have to see that what is more advantageous, to implement. Okay, but that is the idea of the non-contiguous memory allocation. Now we need a hardware support for this. Okay, we need a hardware support, and this is the entire structure of, let's say, paging hardware, where you have a CPU, then you have a logical address generated, and then we have a new term here, in this case is a page table. We'll see what exactly mean, but here after giving this part we will get finally the frame number, and that is your physical address, and that will be go to the directly to the physical memory. Okay, now we have to translate the address. Okay, we have to translate the address, and that is from we have to translate what? Logical address. Okay, address to, we will translate to a physical address. Okay, physical address, and that will be the entire done by the hardware support. Okay, so first is your CPU logical address space, or logical address is generated by the CPU is divided into two parts. Okay, we have two different parts. One is called page number, used as the index of the page table. Okay, now I'll come back to this. What does it mean? Which contain the base address of each page in the physical memory. Okay, that contain the base address of physical memory. So we have a page number, that is the page number part, and another one is the page offset, that is within the page. Okay, so now what is the idea here in this case is, suppose we have suppose, let me take a very simple example. Suppose this is my memory, which is consist of, let's say, 4 pages. Okay, think in this way, that there are 4 pages are there, 0, 1, 2, 3. Okay, and each page consists of 4 information, 4 byte, 1, 2, 3 and 4. Okay, so let me put in a different color here in this case. Okay, so let me just put this 1, 2, 3 and 4. Okay, so 4. So each one is consist of 4 information, or let's say 4 byte. Byte addressability I already explained it. This is byte, these are the bytes. Okay, so now we have page number. So how many pages are there? So there are 4 pages are there, and for that you required 2 bits here. 2 bits in what? 2 bits in the page number part. And how many? And offset means within the page we are talking about which byte. Okay, so there is a 4 bytes are there, and again how many bits required? In that case you can apply simple log of base 2, that is 4. If it is not exact 2 to the power, then seeding function, and that is equal to 2, and that will become your 2 bits. So page number will denote the which page we are referencing. among this, and page offset will denote what? Page offset will denote that which within the page which byte we are referring. Okay, so that is the combination of these two, and this entire thing is a 4-bit, can be implemented as 4-bit logical address space. Okay, so generalization is something like this. If the total of this size is equal to m bits, and you required n bits in the page offset. Okay, for n bits required for what? Now here few constants are there. For 2 to the power n, let's say byte, and byte addressability I'm assuming, so number of bits required is n, and here we are remain with what? M minus n bits. So for logical address space of size 2 to the power m, that is total size. Okay, total size, let's say have byte, and page size 2 to the power n byte. So how many bits here required will be? Log of base 2 to the power n, that will be n bits, and remaining m minus n will go for this page number. The same concept of this division of this page number and the page offset is applied to the physical address space, and whatever the size here in this case, suppose 2 to the power k, and is 2 to the power k is your physical address space, and suppose frame size I keep it same here, that frame size is 2 to the power n, let's say byte. Then here I'll do again this division, that this will become your frame number, and then this will become frame offset. Okay, so this will be of what size? K bits. Okay, sorry, n bits, and here we are left with how many bits we are left? Total is k, and out of that I can take n, so that will become k minus n. So offset within the frame, and this is the index of the frame. Now this thing entirely, this affected by your byte addressability and word addressability. Okay, now here I already told you this definition of being byte addressable and word addressable, but here if one byte has been assigned an address, one byte is one address. Okay, and here we are saying that one word will occupy one address. Okay, one word will be occupy one address. Okay, now this will severely impact what? This will severely impact the offset field. Okay, the offset field. Okay, so let me take few example and let me tell you how does it matter here in this case. Now consider a computer system with 40-bit virtual addressing. Okay, 40-bit, 40. So my logical address space, virtual addressing means logical address space is of the size 40 bits. So this entire thing is 40 bits in size. Page size is 16 kilobyte. Page size, that is a new term. Page size is equal to 16 kilobyte. 2 to the power 4. K is for 2 to the power 10, and B, and that will become 2 to the power 14 bytes. Okay, and it is byte addressable. Okay, now here if it is byte addressable, then it will become this. If it is byte addressable, then we are having the total address space as 40-bit 2 to the power 40 address location, and one address location will be of size 1 byte. Understand this. Okay, so here I have to divide here. This is already written in terms of byte, so we don't need to worry about it. We'll simply take the log of base 2 to the power 14, scaling function of it, and that becomes 14, and I'll make my page offset as 14 bits. Remaining is what? Remaining is 26 bit, and that will become your 26 bits over here. Okay, now same question I am solving with a different with word addressable and word sizes 4 bytes. Okay, so now here the same question is there, but now my address spaces is become larger. This is 2 to the power, this is 40 bits, but if you talk about the entire page 1, then in that case it will become 2 to the power 14 addresses are there, and each will be of size of what? Now it will be size of one word or 40 byte. The address range will become 2 to the power 40 into 2 to the power 2 byte. Then I can say 2 to the power 42 byte. Now page size is 16 kilobyte. Now here in this case is now page size is 16 kilobyte, but now here it is not byte addressable. Okay, it is word addressable. So previously we have got 2 to the power 14, that was because it is byte addressable, but now the question is how many words are there. Okay, how many words are there? So क्या हो जाएगा इसमें 2 to the power 14 divided by, in this case I divided by 4, and that will become 2 to the power 14 divided by 2 to the power 2, and that will become 2 to the power 12. So now here we have 2 to the power 12 words, and to get a single word, number of bits required, how many bits required? To log of base 2 to the power 12, because one address will now refer one word, ceiling function of it. In this case this will become how many bits? 12 bits, and the remaining thing will become, in this case, is 40 bits are there, 28 bits. Okay, so this is how this addressability changes the entire scenario, and this is how the calculation will be done based on your, if it is byte addressable or it is word addressable. Byte addressable 32-bit logical address space. So we have 32-bit logical address space, and here in this case, okay, in this case we are having this as the logical address space, and here 32-bit 4 kilobyte of the pages, 4 into 2 to the power 10 byte, and it is byte addressable, no need to worry. It will become 2 to the power 12 byte, and number of bits here for offset part will become 12 bits. And how many remaining? Total size here in this case is 32 bits, and we are remaining with what? We are remaining with here in this case is 20 bits. Okay, so that is how it has been computed. Okay, few points here that paging itself is a form of dynamic reallocation. Okay, we are dynamically reallocating from one place to another place. Every logical address bound by the paging hardware to some physical address. That is also true. With using paging is similar to using a table with base. Using paging is similar to using a table of base registers, one for each frame in the memory. Okay, so we have a paging means here we are, if you look at the hardware closely, why it is commenting so? It is commenting so because of this diagram. Okay, and what I haven't told you in this case is the page table. So somehow this will go to this, and F will be added with here. So now this page table is what? Page table is nothing but the base address. Base address of what? Base addresses, not only address, base addresses of what? Base address of the frame. Okay, and that is the comment it is making, that it is entirely a dynamic relocation, that you can relocate it dynamically based on the availability. You can relocate anywhere in the memory, and using a paging is similar to a table which is a base address. This is a very important point. When using a paging scheme, we have no external fragmentation. Okay, so now external fragmentation, that space is not enough, that will not come. But any free frame will be allocated to the process needs it, anywhere. However, there will be some internal fragmentation. That is the point I already told you. Okay, so the next part is about dealing into the more onto this. We have a logical address space, and dynamically we can go anywhere in the physical memory, and that is the term, that dynamic reallocation. Okay, so the next part is your paging hardware and the mapping thing. Okay, the mapping, that how we are going to map a logical address to physical address by using logical to physical by using page table. Okay, by using page table. So that's all here. Thank you.